Alright, welcome to Trigonometry. So the idea of these videos is get the theory here and then practice problems in class. So as you can see, today we'll look at applications of trigonometry, and then on Monday the sine rule, and Tuesday cosine rule. Some problems down here that we can use to practice today, and there's this guide for basically what we're going to be doing in this unit. Hopefully put it all together as a picture. Alright, so starting with applications of trig. Okay, we'll remember that trig can be used to find unknown sides and angles of triangles to solve problems in the real world. We have three trigonometric ratios which can be used, but only for right angles. So sine, cosine, and tan. There's the ratios. Some people like to use SOHCAHTOA to remember which ones relate to which. SOHCAHTOA. Okay, so just a quick review of how to do that with right angle triangles. I'll look at these three examples. Okay, so in the first example, we're trying to find an unknown side here. Here's the angle, this is the opposite side, this is the hypotenuse. So I'll look at these rules and decide to use sine to find this side. So right here, use sine, state the rule for sine, opposite over hypotenuse, and then substitute in all the values. I know that the angle is 35 degrees, I know the opposite side is D, and the hypotenuse is 58. So I'll be able to find D by multiplying both sides by 58. Okay, and then I can get approximation on my calculator. Just remember with your calculator, and I think mine will have this issue as well. When you go into run mode, go shift menu and arrow down and make sure the angle's in degrees. So later on we'll do some things in radians, but for the moment we'll use degrees. Okay, so 58 times sine of 35, 33.27. Okay, too easy. Do another example here. So we've got an angle, it's in degrees, minutes, and seconds. Remember, degrees, minutes, and seconds is just another way of dividing angles into smaller parts. There's 60 minutes in a degree and 60 seconds in a minute. I'll do the same thing from this angle. This is the adjacent side, and this is the hypotenuse. Look at my rules. I'll use cosine. Okay, state the rule for cosine, and then substitute in all the values that I know. So cosine, 29 degrees, 35 minutes, 55 seconds equals n on 78. Ooh, made a mistake there. The adjacent side is 78. N. Okay, so to get n by itself, I'll multiply both sides by n. So it's 78 here, and n times cosine 29 degrees, 35 minutes, 55 seconds. And then I'll isolate n by dividing by cosine. Cos 29 degrees, 35 minutes, 55 seconds. How do I type this into the calculator? Okay, same way, so 78. I'll make it so it looks like yours. 78 divided by, I was hoping to get the fraction line, so good. Cosine of, I need to go options, arrow across the angle. So I want 29 degrees, so I'll use the F4 key, 35 minutes, use that same key, and 55 seconds, use the same key. Okay, I got 89.7, is that reasonable? Hypotenuse should be bigger than 78. Yep, looks good, 89.71. There's no units here, but if there were, make sure I write meters or whatever. Okay, so finding the angle, do the same thing. With respect to this angle, that's the opposite side. This is the adjacent side. So I'm going to be using tangent ratio. Okay, or you can just say tan. Write the rule. Tan theta is opposite over adjacent. Put in the values you know. I don't know that angle. Opposite side is 2.6. Adjacent side is 3.7. To get rid of tan, some people try to do some stuff like, I'm going to divide by tan. No, no good, no good. The only way you get rid of tan is by doing the inverse relationship to both sides. So I've got tan there on my calculator. The opposite of tan is tan to the -1. Okay, so that will get rid of the tan from both sides. Okay, so theta will be tan inverse of 2.6 on 3.7. So, go with my calculator, inverse tan of 2.6 on 3.7, 35.1 degrees. What if the paper asks you for degrees, minutes and seconds? Yep, too easy. I'll just press this F5 key and that'll change it backwards and forwards to degrees, minutes and seconds. Fingers crossed. Cool. 35 degrees, 5 minutes, and I'll always round to the nearest second. So 35, 5, and 45. 35, 5, and 45. Any questions? I'm not even here. You're listening to this on the screen. You can't ask questions unless you come into class and ask a question. That's the idea. Alright, so some application problems. So this is all review from Year 10. I taught this to Year 10 a few weeks ago. Angles of elevation and depression. So if I'm standing here looking horizontally, the angle I need to crane my neck up to see that plane is the angle of elevation. So elevation is lifting your head up. For angles of depression, you're up somewhere high, you look horizontally, and then arch your neck downwards, and that'll be the angle of depression. And this relationship is important as well, that the angle of depression and the angle of elevation is the same. So this person down at A is looking up at the same angle that person at B is looking down. Alright, so we'll do one of these problems. From a rescue helicopter 1800 metres above the ocean, the angles of depression of 2 shipwreck survivors are 60 degrees and 40 degrees. We need to calculate how far apart the 2 survivors are. Okay, so part A, we'll draw the situation. So draw my plane. Draw your plane. It is 1800 metres above the ocean. Okay, here's the ocean. And there's 2 survivors. So there's one where from the plane, from that horizontal direction rather, you need to look down 40 degrees. Okay, we'll call that survivor B. And there's another survivor that you need to look down 60 degrees. We'll call that survivor A. So when you're drawing diagrams, always label them. Okay, and label these important points as well. So I've got a right angle down here, which will be useful. Might as well call that C, might as well call that D. So the skills that we have, what are we trying to find? How far apart the 2 survivors are. So I'm trying to find this distance X. Okay, I can't do anything with this triangle DAB. Okay, can't do it because none of these angles are right angles. Okay, so I'm searching for right angle triangles. Okay, so I can see two right angle triangles. I can see one small one, DCA, and I can see one big one, DCB. Okay, so I'm going to calculate two distances to find x. Okay, I'm first going to calculate what's the distance from where the plane is on the ocean to the first survivor. Okay, I'll call that y, and then I'll calculate this whole distance from where the plane is to the second survivor. I'll call that, I don't like using z, so I'll just call that p. Okay, don't use z's because z's look really close to 2's. And I'm just going to find those two distances using two right angle triangles. Okay, so to find y, for starters, I'm going to use triangle CDA. So always state which triangle you're using and then just draw a little image of what it looks like. It doesn't need to be particularly neat. And this is y. So I know that the angle of depression is 60 degrees. So I know this angle at the top will be 30 degrees. Okay, because they both have to add up to 90 degrees. Alternatively, you could say, well, angle of depression is 60 degrees, so this also is 60 degrees, and you can use that angle. Either way, it doesn't matter. Okay, I'm just going to use the angle at top. You can do whatever you want. Okay, so make sure you label this as well. In the bigger problems, you'll get lost if you don't do this. So from 30 degrees, I've got an opposite and an adjacent side. So I'm going to use tangent, which is tan. Okay, opposite and adjacent, and just power through here, through the details. This should be pretty routine for Maths B students. Okay, and we can find an approximate value for y. Okay, 1039.23 meters. Okay, so now I'm going to find that larger value, p. Okay, so to find p, we'll use triangle DCB, which is the really big one. 1800. Better label it DCB. This is P down the bottom. Do I know any of these angles? Just for fun this time, instead of putting 50 degrees up where D is, I'll instead put the 40 degrees down here. Okay, it doesn't matter which one I put in there, as long as I put an angle in there. Okay, again, opposite and adjacent. Remember, it's always from the point of view of that angle. So again, I'm going to use tan, use the tangent ratio, which is tan theta opposite over adjacent. So tan 40 is 1800 over p. Oop, there's the unknown on the denominator, so I better go through my drills, bring p to the other side by multiplying by p, and then divide through by tan 40. Okay, so calculator time again. Someone's playing a video in the room next door. Hopefully that's not audible on here. So 2145.16. 2145.16 meters. Okay, so the distance between the two survivors is going to be the difference between those two distances. Okay, and I'll just write that logic in. Distance between survivors is P minus Y. Slot in these two values, 2145.16, take away 1039.23. This is hard, actually doing all the calculator work. (1105.93). Okay, so they're 1105.93 meters, and I'll write some statement like that as well. They are 1105.93 meters apart. Okay, part A done. Part B, state any assumptions made and their associated effects. So, assumptions that we've made when drawing this diagram essentially are that the plane, that's a plane, and the two survivors are all in a straight line. Okay, so it's not like B is over here somewhere. We've assumed that they're all in a straight line, so we can just draw that from side on. Okay, so that's the assumption. The effect is, if that wasn't true, then our distances calculated would be shorter than it would be in reality. Okay, that is the distance we have. If B is anywhere but in a straight line, it'll be a longer distance between A and B. Okay, so one assumption is that the plane A and B are in a straight line. Okay, and the effect of that was, if not true, the distances would be incorrect. Okay, specifically, A to B would be longer. Okay, that's one assumption that we made. The other assumption is that the thing from A to B is flat. Okay, we drew that flat, we're assuming it's flat. Okay, we assume A to B is flat. Okay, the ocean is pretty flat, so it's reasonable to assume. A lot of these problems we'll do on land where that's not the case, or could potentially not be the case. And if we do problems on a bigger scale, we know that the Earth is round, not flat. So if I was doing the same problem but the survivors were 100 kilometers away, you might get a little bit of a chord there instead of the real arc around the Earth that you should. Okay, so assume A to B is flat. If that's not true, okay, then the distances will be wrong as well. Okay, in this case, all of them will be longer than calculated. Okay, so in modelling problem solving questions, it is in the syllabus that you need to be able to answer questions like that. Okay, so there's some bearings done and some review. Sorry, some angles of elevation and depression done and some review. We'll look at some bearings problems, so quick review of what bearings is all about. We've got compass directions and we've got true bearings. So in the case of compass directions, it's measured as the distance east or west from the north-south line. So this, and it's always from a starting point. So if I'm going to say I'm going to walk south 20 degrees east, from this starting point, I'm drawing an arrow the direction that I'm walking. Okay, if I lined up north and south in my direction of walk, I'm going basically south, but veering a little bit to the east. I'm going 20 degrees to the east. Okay, similarly, in the second diagram, I'm starting at this point, I'm walking up north, I'm not going directly north, I'm sort of veering 40 degrees west. Okay, the temptation for some students is if you have a direction out here somewhere and this is 40 degrees, they'll want to call this east 40 degrees north. Okay, can't do that. Okay, it always needs to start with north or south and then the angle that you're going east or west. All good? Okay, and true bearings is measured from north in a clockwise direction, always using 3 digits. So whichever direction I'm going, I'm starting at north, drawing a line to where we're actually going, and measure that clockwise direction. In this case, we've only gone 25 degrees away from north in a clockwise direction. Okay, so 0 to 5 degrees true, okay, because it always needs to use 3 digits. In this case, we're going like in the southwest area, from north, measure that clockwise angle all the way around, it's 250 degrees. Okay, so you're expected to be able to convert between the two systems as well. So for instance, if I wanted to write this first compass direction as a bearing, okay, I'd look at, all right, from north, I'm going around. I know that generally north, east, south, west, I know this is 90 degrees, this is 180 degrees, this is 270 degrees, this is 360 degrees. I know south is 180, so 180 minus 20 is the same as 160 degrees true. Okay, so you need to be able to do those conversions. This one here, well, I would need to start at north and go all the way around clockwise. So I've almost gone around the full 360, I'm just 40 degrees short, so this will be 320 degrees true. In a similar fashion, I should be able to convert this. Well, from north, I've gone 25 degrees east, and here, from south, I've gone 70 degrees west. Okay, so south, 70 degrees west. How did I get to 70? I know all to here is 180. 250 all the way around, difference between those two is 70. Okay, so this question says write both of them as compass bearings and true bearings. Press pause and have a go at writing both as compass and true bearing. Press pause. Pause. Alright, so you've had a go at doing that. Alright, so as a compass bearing, this one from south, okay, we're going 58 degrees east. And as a true bearing, from north, I'm coming around here. So I'm not going all the way to south, which is 180 degrees. So let's do 180 minus 58, whatever that is. It'll be 122 degrees true. Okay, this one over here as the compass bearing. Okay, from north, what's this direction here? Well, it's not 13 degrees. I know the whole thing adds to 90. It should be 77 degrees. Okay, so as a compass bearing, it's north, 77 degrees west. And as a true bearing, what angle do I go around clockwise from north? Well, I'm not going the whole way around 360. I'm stopping short 77 degrees. So whatever 360 minus 77 is. Okay, which will give me 283 degrees. Okay, alternate way of finding that would be just to go up here to 270 degrees and add 13. Okay, sure, I got it right. Okay, so the reason why we teach you compass, directions and true bearings is because in problems that we want you to solve, you're required to do those sorts of calculations. Okay, so looking at one example here of John leaving a campsite and hiking in a certain direction and changing directions and walking another distance at another direction. Okay, we want to be able to draw this and have an idea of what's going on and solve these problems. Okay, so have a read through the problem, press pause if you want. Part A, how far does Alana have to hike and at what bearing? So Alana's still at the campsite, John's gone for a walk, Alana wants to just walk directly to where John is. So we'll start at this point. So always draw a compass rose at each point. He leaves the campsite and hikes 3 kilometers at 40 degrees. Okay, so he's going 3 kilometers at 40 degrees from north. And then he changes direction and walks. Should make that a little bit shorter. Changes direction. So I'll call this C for the campsite. Call this D. Changes direction and walks for 5 kilometers. At a bearing of 80 degrees. Okay, so the question is, how far does Alana have to walk? Okay, John is here. How far does she have to walk if she just wants to go in a direct straight line to see her friend John for lunch? Okay, that triangle that I've drawn here, no trig is going to help me there because it's a non-right angle triangle. So I'll erase this. Okay, where we're going to work this out is find, first of all, how far east that John travelled. Okay, so just finding this horizontal distance and this horizontal distance, so x and y, and then find in part 2 how far north that John travelled, okay, which will be this height here, call it A, and this part here B, so that we'll be able to just draw. We'll be able to just draw from the campsite to John one straight line. This distance here will be x plus y, and this distance here will be a plus b. Okay, so we'll need to use a bit of trigonometry for this. Okay, so how far east John travelled? Well, I'm going to have all these right angle triangles. I'll call this point E, call this point F. I need to use triangle CDE first. Okay, so I'll draw what triangle CDE looks like. That's 40 degrees, so this part in here needs to be 50 degrees. Okay, I've got 3 kilometers on top. I'm trying to find that distance, CDE. Okay, so you can go ahead and do that. And also going to use triangle DFJ, okay, to find y. DFJ. Okay, so to find y, this is 5 kilometers. Since he's going at 80 degrees, that's 10 degrees there. Okay, so in both cases, going to be using cosine, okay, because we've got adjacent and hypotenuse, adjacent and hypotenuse. Okay, so write the rule, cos theta, adjacent over hypotenuse, cos 50, x on 3, x equals 3 cos 50, and over here will be the same thing, cos 10. Don't be lazy, always write the rule. Okay, and if I add these two together, I'll find how far east John travelled to be able to put on my diagram down here. Okay, so yeah, I don't know what this is. There we go to the calculator. Cos 50 plus 5 cos 10. Okay, put that in the calculator. Okay, 6.85. Okay, and do the same thing for these distances north. Okay, so same triangle, 50 degrees after Y this time. Sorry, I'm after A for the two distances north. This is the same triangle DJF. So you can probably combine your working for both of these, but it's important that you label all these triangles and actually draw them down so you can refer to them and not get lost along the way. Okay, so cos theta, I'm not using cosine now. Okay, don't be lazy. Opposite and hypotenuse. Opposite and hypotenuse. Sine theta is opposite over hypotenuse. Okay, so sine of 50 degrees, A on 3. So A is 3 sine 50. Again, over here, same deal, sine rule. Always write the rule. So B on 5, should be able to rearrange this for B. Okay, so this total distance here will be 3 sine 50 plus 5 sine 10. Okay, you can use decimal approximations all the way if you want, but we prefer you use exact values. Okay, 3.17. Okay, so I've simplified that journey into just one big right angle triangle. That's the whole idea. Okay, how far does the liner have to hike? Part B. So CJ, I'll call this G. In this big triangle, CJG, that's 6.85, that's 3.17. This is unknown here. Okay, better give it a different letter. May as well call it C, lowercase c. Okay, we'll just use Pythagoras here. Okay, A, B, and C. So use Pythagoras. Okay, A squared plus B squared equals C squared. And I'll sub these values in. So 3.17 squared plus 6.85 squared equals C squared. If your variable here is not C, like say you've got, actually I'll change this to D, just so I can illustrate this point. If you've labelled this variable as D, then you should change the C to a D here as well, just so it's relevant to the problem. Okay, take square root of both sides, always plus or minus square root. Okay, so type this in. Okay, so 7.55 kilometers, plus or minus 7.55. Okay, always reject D equals minus 7.55 as negative distance, has no meaning in here. Alright, so I'm going to write some statement here. She has to walk 7.55 kilometers. And at what bearing, too many words in this problem. Okay, what bearing, I can find this angle. Okay, and that'll help me find the bearing from north. Okay, so I'll find this angle using tan. Okay, opposite over adjacent. The values we know, and now this is the opposite and the adjacent side. 3.17 over 6.85. So that angle will be angle's 24.83 degrees. Okay, but remember what I've found is this 24.83 degrees. I want a bearing from north, so the bearing will be 90 minus that angle. Okay, so I've already got that angle in there, so 90 minus that answer, shift answer, 65.17. Okay, so the bearing is 0.65 degrees true. Now what bearing would they have to follow to return directly to the campsite from their lunch spot? Alright, so in this diagram we've got them walking at 65 degrees. Okay, so from the campsite, so we calculated that arrow there. What we're going to find is what would the direction back be. Okay, again, draw some compass rose. I want to go all the way around here. I know that this angle in here, this small one, is also 65 degrees. Okay, because I have a Z forming in this red region. Okay, remember the Z's, those two angles are always the same. So the bearing back will be 180 degrees, okay, from north to south, plus that 65 degrees. Okay, so 245 degrees true. But see, identify any assumptions and their associated effects. Okay, similarly as the previous one, assume that the ground is flat. Okay, if not, distance calculated would not be correct. Okay, we also assumed that they actually walk in a straight line. Okay, which is pretty hard to do out there in the bush. Alright, so there is drawing in 3D as well, but I'm going to have to take a little break and then do that next one